Okay, well, welcome everyone. Today we're going to be talking about bearing failure mechanisms, and we're happy to have our good friend Andy Page from Allied Reliability Group back to talk to us about bearings. I'm not sure there's a topic we throw out there that garners as much interest as bearings do. It's a good thing we do this in a webinar format, because I think we'd have standing room only if we were in a conference room somewhere. Before we start, just a little bit about UE systems. We've been in this ultrasound world for 40 years now, and while obviously leak detection was sort of the start of it all, I think it's safe to say that over these 40 years we've really evolved, and now we're able to do all kinds of things with electrical analysis, obviously mechanical inspections and bearings and lubrication, and it's really just become a really great tool and continues to help folks throughout the world to take care of their assets in a cost-efficient way and keep everything running the way it's supposed to. If anybody's interested in some additional information about UE systems and what we have to offer, just pop me a little note in the questions box, and I'll be happy to email you our interactive information guide so you can get a little bit more details about all the different products that we have, the applications they cover, and all that good stuff. So I'd be happy to share that with you. And just a couple housekeeping things before I toss this over to Andy. Just like all of our webinars, if you've participated in the past, we are recording this, so we will be able to post this on our website. We'll probably have it up in a couple days, so if you have to pop out or you've got a colleague that you think really should have participated and listened in, they'll certainly have that opportunity after we get this online. There is the opportunity to ask questions, so like I said about asking for that information, just pop me a note in the questions box, and throughout the webinar, if it makes sense, I'll stop Andy and get your question answered, or of course we'll obviously have the typical Q&A at the end of the session. So without further ado, I'm going to toss the screen over to Andy here and let him take things away.
Okay, great. Thank you, Maureen. Appreciate that. Okay, my name is Andy Page. I work for a company called Allied Reliability Group, or GP Allied, as we're sometimes known, and we are a reliability training, education, and consulting company. So this presentation here is on bearings, specifically the way bearings fail and things we can do from a condition monitoring standpoint, a precision skill standpoint to help us with our bearings. So if at any time somebody has a question, just fire a question into the chat box, and Maureen will catch them and hit me with them from time to time. So happy to answer any questions. Okay, so let's get into it. To understand bearings, we got to understand the way they fail, and before we understand the way they fail, we have to understand how they work. So, we've got the green box here is a cutaway version of the outer race, and the yellow balls represent the balls or rollers in a typical bearing. So, as the rotor puts weight on the shaft, and the shaft puts weight on the inner race puts weight on the rollers, and the rollers transfer their weight to the outer race, what happens underneath each roller is what we call a stress cone, or area of stress concentration. So the highest stress concentration is directly below the center line of the ball or roller. As you can see, that's where it's the highest. And if we move left and right, it gets a little smaller and a little smaller and a little smaller. So as the rollers pass through the load zone, they're taking those stress concentrations with them. Now once they move out of the load zone, there is no stress concentration. So that's our first kind of learning point about bearings. When we collect vibration data, when we collect ultrasonic data, we want to have our sensor in the load zone, or as close to the load zone as we can get. Now, some of you are saying, hey, Andy, high frequency information is omnidirectional. I can pretty much stick my sensor anywhere and pick it up. That's mostly true. But if we can get our sensor in the load zone, the data transfer is just better. So We see that a lot of mistakes people make when they permanently mount a sensor on a bearing, let's say on a large critical conveyor or something like that. They want to monitor it 24/7, and the bearing is not located anywhere near the load zone. So there's a real good chance that there can be an issue with the bearing, and we not find it till later on. So if you can imagine these rollers moving, they take those stress concentrations with them. So as we're in between the rollers or the bearings, there is no compression of the face of the outer race or compression of the face of the inner race. So as each ball or bearing, or roller, excuse me, moves through a particular spot in the load zone, there's all these compression relief cycles. So as the ball passes, it compresses. As it rolls over it, it relieves. Compress, relief, compress, relief, compress, relief, compress, relief. So if we take a typical motor turning 1,775 RPMs or 29.6 revolutions per second, and those of you who know about vibration know that in one rotation of the inner race, not every ball passes a given spot on the inner race or outer race, whichever one you're talking about. And so the one we'll use here, in one rotation of the inner race, on a given spot on the, one rotation of the shaft on a given spot of the inner race, we'll have 8.193 balls pass that spot. So if we look at how many times that happens a day, it's 21 million times. If we look at how many times that happens a year, it's 7.5 billion times. So one of the big misconceptions out there about bearings is that bearings can last forever. Well, that's not really true. As we look at how often a spot on a piece of steel gets compress, relieve, there's a limit. There's a limit to how many compression relief cycles it will handle before it breaks. And when it breaks, we're able to detect it using things like vibration analysis or ultrasonic analysis to find those inner race defects, outer race defects, ball defects, cage defects. Now, the way we find those, we've got to know a little something about the bearing itself. If we know the number of balls or rollers, roller diameter, pitch diameter of the bearing, contact angle of the bearing, and shaft speed, we can punch it into equations like this that your vibration analysis software does for you. And what we learned that each individual part of the bearing has a distinct frequency it gives off, if you will, once a defect has formed on that particular part of the bearing.
Hey, Andy, sorry, I was just going to interrupt you real quick. I think the little go-to webinar like toolbox, I think you've got that kind of in the upper left-hand corner.
Oh, I didn't even know you guys could see that.
Well, usually you're not supposed to be able to, but for some reason it's showing just a black box, and so I think it was covering some of the information you had on your slide. But that's better.
Is that
Thank
better
you.
Now?
Yep.
Okay.
Thanks.
Good point. Yeah. I was like, I left it there. I said, oh, you guys can't see that. So, okay. So, contrary to popular belief, or what used to be very, very popular belief, vibration analysis is not is science. It's not art. There are equations. There are specific frequencies we look for. Those frequencies develop patterns. Those patterns tell us about different faults within the drivetrain of the machine, and those faults equate to specific problems once we start taking things apart. Right. So I think it's important to note here at this point as well that what used to be a very big misconception about this thing called a baseline, and people who are not educated about vibration and ultrasound to a large degree still think that oh, we got to have the baseline. If you don't have the baseline, you can't tell if there's a problem. Well, that's not true. That was true back before microprocessors got cheap. That was true back before we had spectral analysis capabilities. Way back in the, say, prior to 1986, really, 1984 officially, but prior to 1984, we didn't have spectral capabilities. These equations didn't really help us because we weren't able to see individual frequencies in the vibration signature. We were only able to see an overall number. So that overall number would go out and we'd place our sensor on the bearing and we'd press the button and the needle would come over to a spot on the analog gauge, and we would write that number down. And then next month we'd go back to that same spot. We'd try to replicate the same conditions. We'd hit that button, and we would hope that that needle went to the same spot or worse. Because if it went to some number less than what it was last month, how do we explain how this machine is getting better, right? That was our only explanation at the time. Well, with spectral analysis, we don't have to do any of that business anymore. This could be the very first time we've analyzed the vibration signature of a blower. We could literally not know anything but shaft speed, and we can very accurately determine whether or not there's a bearing fault, and to a large degree how severe that bearing fault is, using equations like this and using spectral capabilities. So with a few notable exceptions, the concept of a baseline is really no longer necessary. Now we tend to think of it as a commissioning analysis. We just worked on this machine. Let's take the vibration, let's take the ultrasound, let's take the infrared, let's take the motor circuit tester, let's pull an oil sample, let's make sure that all the conditions associated with this mechanical drivetrain are correct before we give it to operations and say this machine's healthy and this machine's ready to go. All right, so the reason we look for those bearing fault frequencies, again, going back to our rollers and their compression relief cycles, is we know that if we compression relieve steel enough times, it will eventually reach what's called its fatigue load limit. And you will develop this thing called subsurface fatigue. And this is where there is ultra-high frequency vibration going on, ultra-high frequency signatures coming from the drivetrain that is easily detected with ultrasound and easily detected with your more modern vibration analysis equipment. Nothing has chipped off of the surface of the race yet, so oil analysis doesn't really help us at this point. However, there is a tremendous amount of high-frequency energy coming from the bearing, and that high-frequency energy comes from the balls or rollers are still rolling across there. They're still compressing, but now inside every one of those little cracks, I've got relative motion. And where I have tiny bits of relative motion under a high stress load, that will produce super high-frequency noise and vibration. So if we leave that subsurface fatigue and we keep, the rollers keep coming by and they keep doing their compress relief cycle, eventually all of those little cracks will connect. And when they get connected well enough, they pop out. And when they pop out, we now have spalling. So if we go back to the subsurface fatigue, at this point we can't hear it with the ear. It's super high frequency. Infrared doesn't help us because the bearing's not hot. Motor circuit analysis certainly doesn't help us here. Oil analysis doesn't help us here because nothing has broken loose from the bearing to be found in the oil analysis if it's an oil lubricated bearing. All we're really down to is ultrasound and vibration. Vibration will show if it's an outer race defect or inner race defect. Vibration will show the outer and inner race frequencies. At this point, ultrasound, it's very interesting characteristic in ultrasound. It still sounds smooth, but it's very loud. And this is a mistake that a lot of people who are just got their ultrasonic instrument, this is a mistake they make when they're listening to the bearings and it sounds quiet and smooth, and the next one's quiet and smooth, and the next one's quiet and smooth, and then we get to the next one. It's loud, very, very loud, but still smooth in terms of pattern. So they reach up and they turn their sensitivity down or their volume down or whichever instrument they have and whatever's labeled, but they'll turn it down to something that sounds about the same as the previous four, and they go, okay, well, that still sounds smooth. And then when they move to the very next bearing, they can't hear it at all, so they turn their sensitivity or their volume up, and they go, okay, that one sounds smooth too, and they keep progressing along their route as if all things are good. Well, the one that was loud and smooth was trying to tell you something. It was trying to tell you that this subsurface fatigue exists and that you have just identified a very early bearing fault. So one of the things we like to teach people or encourage people is when you set out to do a mechanical ultrasound route where you go listening for rotating things, you go listening for bearings from blowers and motors and gearboxes and pumps and what have you, set that frequency range correct, somewhere between 20 and 25 kilohertz. Set that volume at some place where a healthy bearing is, you can hear it and it's smooth, and then leave the sensitivity or the volume alone. Because when you get to that bearing that's smooth and loud, it's trying to tell you something. And you should note that as this bearing has a problem. Right? Okay, so now, once the spalling occurs, we've got real problems. Material has now started to remove itself from the face of the inner and outer race, or the face of the balls, or even the face of the cage in some instances. And it's now present in the oil sample if we can get a representative sample. The vibration, of course, is going crazy. The ultrasound is going crazy. If we leave the spalling long enough, it actually starts to accelerate at the rate at which it's getting worse. And that's the reason the P to F curve, which is coming up, is a curve and not a line. It took a long time for that subsurface fatigue to develop. It took a long time for that subsurface fatigue to become spalling. But by the time it becomes spalling, it won't be very long, relatively speaking to the first part of the curve. It won't be very long until the bearing is in really bad condition. So the spalling propagates through the load zone very, very, very rapidly. So our first sign of trouble then is that subsurface fatigue. And if we were thinking about the things that accelerate the subsurface fatigue, things like imbalance, misalignment, V-belts being too tight or misaligned, broken bolts, loose bolts, broken welds, overload, overspeed, shock load, all of the things that increase the radial and axial load on the bearings above and beyond that which they're designed to do from normal operation. These are the accelerators to that failure mechanism called fatigue. So if you want to, you can't eliminate fatigue, but you can reduce the instances of fatigue, and you can certainly eliminate all of these things as accelerators of fatigue. And you can push point P really, really far out in the future if you can eliminate all of these things that we call accelerators. So that's the way a bearing, we'll say, mechanically fails. The way a bearing chemically fails is a little bit different. So if we come back to our concept of lubrication, you'll see this big triangle here between the roller and the race. That's the gross exaggeration of the thing called a lubricant wedge. So when the conditions are correct inside the bearing, the ball, the roller, really never, while it's running, the roller never touches the inner race or outer race. It actually rides on these things called lubricant wedges. And these lubricant wedges form because there's a high pressure area there between the roller and the race, and lubricant is not compressible. So as we try to put pressure on the lubricant, the physical characteristic, one of the physical characteristics of the lubricant changes. Its viscosity changes. And if we put enough pressure on it, the viscosity of the lubricant can get so hard that it's actually able to physically keep the roller and races from touching each other. So that lubricant wedge is a very, very important thing for us. So if we've got oxygen and steel and heat, what we will get is a thin film of iron oxide. This thin film of iron oxide is this soft, relatively soft, softer than the parent metal, soft material that forms a very, very thin layer. You can't see it. It's only 3 microns thick. A very, very thin layer of iron oxide. And that's the thin, soft layer of iron oxide. That's what that lubricant wedge rides on. So as that lubricant wedge rides on that soft film of iron oxide, what's happening is it's rolling up little pieces of iron oxide. You can imagine when your hands are dirty, if you put your palms together and you press them real hard and you start rubbing, little balls of dirt fall out. Now, once your hands are clean, if I did that same thing and I pressed my palms together, specifically those pads right there where your fingers connect to your palm, if I push those pads together and I press really hard and I rub them back and forth really fast, little balls of skin start to fall out. This is called adhesive wear or two-bodied wear. That's what's going on here. The lubricant wedge rides on top of that thin film of iron oxide, and it rolls up little balls of that iron oxide and expels them outside of the bearing. Or the grease will remove them from the surface eventually. So you can imagine then, as that lubricant wedge rides over that thin film of iron oxide, that film of iron oxide gets a little thinner, a little thinner, a little thinner. Well, as it gets too thin, the chemical reaction between the heat and the oxygen and the steel happens again, and it just reaches down and grabs another layer of the parent material. So you can imagine then over time, the internal radial clinches of the bearing opens up. It gets loose. This is what bearings are supposed to do. This is a major misconception with folks that bearings can last forever. No, they don't. Either fatigue gets you or adhesive wear gets you. And both are normal. We expect the bearings to do that. And we expect them to do that for somewhere between 8 and 12 years for the garden variety bearing in the correct application. So 20 years is unreasonable expectation for ball bearings or roller bearings. 20 years is nothing for sleeve bearing, but we're not talking about sleeve bearings. We're talking about roller bearing or ball bearing, either one. So you can imagine then what happens if water gets in our bearing. Well, first of all, the lubricity of water is extremely poor. So just off the cuff, if we have more water in there than we have lubricant, or if we have enough water to affect the lubricity of the mixture, then we have a poor lubricant. And then secondly, without getting into the laws of thermodynamics and all that business that people love to get into, if we get enough water in that lubricant wedge and we get that water hot enough, it becomes compressible because it's no longer water, it turns to water vapor, and the lubricant wedge can't form. And when the lubricant wedge can't form, we've got a problem because now the rover's riding directly on the race, and that's bad. So this is called the saturation point of lubricant, the percentage of water that happens before that lubricant wedge, or EHD, cannot form, cannot happen. So if we think about all the things that accelerate adhesive wear, if I put too light a lubricant in there and that lubricant wedge isn't strong enough to hold the load, then I'm going to accelerate it. If the lubricant's too heavy and the molecule is just too big, if you will, to fit in the hole, then it's the same as not having any grease in there. Or if I get water in there, that's going to accelerate it. Last failure mechanism we'll talk about before we talk about some of the other PDM stuff is contaminant, abrasive wear. So our old example of our two palms on our hands together, if I got one palm wet and dropped it in a pile of sand, and then I put my palms together again and started rubbing them, now skin falls out much faster because I have my two palms and I have sand. So I now have what's called three-bodied wear. Sand makes the third body, or abrasive wear. So poor contamination control techniques in the way we sample lubricant, in the way we top off our lubricants, in the way we store our lubricants, ingest, or we allow contaminants to be ingested into the bearings or the gears, and we get this condition here. So here's our little piece of silica, and it doesn't have to be very big. If it's larger than that lubricant film, it's a problem, and that lubricant film, remember, is only about 3 microns big. So if that lubricant wedge, I guess some of the times it can hit that thing and knock it out of the way. Other times it's going to grab it and it's going to plow with it. And when it plows with it, it's going to produce little cuttings exactly like lie on the floor around a lathe or a mill, except smaller. And those little cuttings are the results of contaminant or abrasive wear. So things that we do that accelerate abrasive wear, you know, allowing a blown seal to continue on a machine. Poor lubricant handling practices, poor lubricant procedures, poor lubricant storing practices, poor sampling procedures. If we sample in a way that allows contaminants to be ingested into the machine, or the machine to ingest contaminants, then, you know, all of the way we interact with our lubricant and the way that we interact with our machine is by and large the culprit for this thing called abrasive wear. So if we want to extend the life of our bearings, we've got to look at those accelerators for abrasive wear, adhesive wear, fatigue, and we've got to go all-out war against eliminating as many of those as we possibly can. Now, there are other failure mechanisms like corrosive wear and things of that nature, but if we look at the lion's share of the things that cause bearing issues in industrial applications, it's fatigue, abrasive wear, and adhesive wear. So one of the things that people love to talk about in the condition monitoring world with respect to bearings is this concept of slow speed analysis. And one of the questions we get all of the time is, which is better for slow speed analysis, vibration or ultrasound? Right? We get that question a lot. And the answer is that both are powerful inspection methods. Both are excellent for slow speed analysis of rolling element bearings, but there is a technical note, right? The time capture has to be sufficiently long regardless of the method you're using. Let me say that again. That's important. This is an important point. The time capture has to be sufficiently long regardless of the method you're using. Let me go into an example. So if we look at very slow speed bearings, you know, less than 20 RPMs, cage faults tend to happen first on ultra slow speed bearings, because what happens is due to the very, very low speed, usually very, very high loads, the rollers will skid instead of roll. This is very typical in super slow speed bearings. So when they skid, especially when they skid through the load zone, they'll damage the cage first. The cage gets damaged the quickest. So if we want to look for cage, which is a subsynchronous fault, for those of you unfamiliar with that term, subsynchronous means it happens less than once per revolution of the shaft. So for subsynchronous faults, we've got to have a method to find those subsynchronous faults. So cage frequency is the lowest of them all. It's less than turning speed. And in general, most bearings, cage, you'll hear cage once every 3 revolutions. So if I want to resolve cage in the spectrum, if I want to be able to see the cage frequency in the spectrum, then I need at least 4 data points. The spectral analysis, the FFT process works basic statistics. I've got to have 4 data points before the FFT will recognize that as a, yes, that's a frequency that is of note, and I should display that in the spectrum here in a moment. So if I need 4 revolutions of the shaft to hear it once, and it happens about every 3 revolutions, then to find cage, I need 12 revolutions of the shaft. Now notice I haven't differentiated ultrasound from vibration yet. Doesn't matter. Still need 12 revolutions of the shaft if I'm going to find cage. So if a shaft's turning 9 RPMs, the time capture's got to be 1.33 minutes. That means I'm collecting data, whether I'm doing vibration or ultrasound, for 1.33 minutes. So if you're trying to do this without spectral capabilities on your, let's say your UE 10,000 or 15,000, or even some of the other ones if you've got them physically connected to a vibration data collector, if you're trying to do this with just your headphones, it's going to be really, really, really challenging, because I have to listen for 1.33 minutes, and I have to be able to distinguish 4 similar sounds that are equidistant apart during those 1.33 minutes. And anybody that says they can do that, I'd have loved it for you to show me how, because that is challenging. So that's why we use a spectrum, which it also means I cannot listen to a bearing for 10 to 15 or even 20 or 30 seconds and walk away from there going, oh yeah, we've got a cage fault here. Now, if we have an outer race fault or an inner race fault, yeah, you can listen for 10 to 15 seconds. It's not a problem, right? Because those are happening somewhere between 3 times per revolution and 15 times per revolution. So hearing it just 4 times to resolve it in the spectrum is no problem. Right? So we got to have spectral analysis. So to the subject of, which is better for slow speed bearings, vibration, or ultrasound, I would put it to you this way. It becomes a function of criticality. If you have a supercritical bearing where you need all of the information you can get as early as you can get, I would encourage you to consider vibration. For the bearings that aren't supercritical, where cage faults don't bother me as long as I know about the inner and outer race faults, then just using one or the other would be perfect. The best application is to use both. And now from this example, hopefully this example helps you understand why and how vibration can be so powerful on something running slow speed. Here's an example. Here's a bearing turning, it says 10, I recall it being 9, but okay, we'll call it 10 RPMs on a trunnion bearing of a large rotary vessel. So you can, one bearing is very, very healthy. The waveform at the bottom shows nothing. The spectrum at the top shows nothing. Now you'll note that I've fixed the scale so that they look that way. Well, the reason I fixed the scale is when I compare it to the next one, which is the bearing on the other end of the same shaft, it looks like that. Now you'll note, if you want to pay attention, the scale's the same, 0.06 on the spectrum at the top and 0.8 on the waveform at the bottom. So when I move to this one, the scale's the same. So this is a bit of a lesson for those of you who are not really tuned into vibration analysis. If you're going to compare spectrum and waveform, set the scales the same. And that way the height of the peak becomes relative comparison to the other spectrum or waveform. So here you can see the spectrum's quite clean. You can see the little gray or white boxes on top of the peaks there. We've identified an inter-race bearing fault. It's very, very clean, very clear, very easy to see, and you can see in the waveform the nastiness as those balls pass through the load zone, or the bad spot in the load zone with every revolution. So vibration can be quite powerful if you got your setup right and got the right equipment. Maureen, do we have any questions to cover before we move into the next section?
Yeah, I mean, just a couple people wanted some clarification, and I didn't notice if they asked it before you kind of made some of your comments or after, but just if you can reiterate what you consider to be slow speed and what you consider to be ultra slow speed when you're talking about this.
Oh, that's one of the great loaded questions of the vibration world, or excuse me, of the condition monitoring world. Ask 10 different people, you get 11 different definitions. In general, as I recall, now this is not the world according to Andy, this is just things I recall, most people consider anything less than 100 RPMs slow speed, and anything less than, pick a number, 30, 40, 50 RPMs ultra slow speed. But that's just, that's a bit like spicy and beautiful. It's very relative to the eye of the beholder, if you know what I mean.
Yeah.
So the good news is the setup for vibration and for ultrasound does not matter for speed. If you put in speed into your equation for the setup and it spits out, Fmax and all that other business, the rules, that's what I should have said, the rules are the same. So, before 1996, those who were in the vibration world before 1996, slow speed was a major, major pain in the rear. But since 1996, and for those of you who are not tuned into it, 1996, what happened to the vibration world is envelope demodulation became popular. And envelope demodulation is the thing that helps us overcome what used to be speed limitations with respect to slow speed stuff. right? So, flipping that little switch in the software as you build your route and makes a big difference in our ability to analyze data on bearings turning less than full speed. So we'll stop differentiating between slow and ultra slow. That's really we used to worry about those definitions, but because of the advancements in vibration and ultrasound as well, we don't worry about making that distinction anymore. The slowest I've ever done is the one you just saw, the 10 RPMs. The slowest I've ever seen is 1/3 of an RPM, and it pretty much looked exactly like that one. Interrace fault, clear as a bell, lots of activity in the waveform. When you compare the good bearing to a bad bearing, drastic differences, easy to spot, easy to see. And we don't really worry about the distinction between ultra slow, slow, kind of slow, moderately slow, and full speed. We don't worry about that.
All right, sounds good. And there were a couple other folks looking for some sound examples and some illustrations of the different sounds, but I'll be able to get those things offline.
Yeah.
So for those of you
who guys are the best resource for that. Yep.
Great. All right, carry on, sir.
Okay, cool. So let's look at this thing called fault progression, and if we look at this, the relationship between bearings and grease, we got to ask ourselves, do bearings? I love this question because when I first started forming it in my head, I was like, all right, do bearings consume grease? And of course, the answer is, no, bearings don't consume grease. But then you ask the question, well, if they don't consume grease, why do we have to keep adding grease to the bearing? Right? So the answer is bearings don't consume grease. Bearings expel grease. One of the jobs of lubricant is to remove heat and contaminants from the load zone, and the rate at which it does that is a function of speed, load, temperature, and humidity. So if we think about how often speed, load, temperature, and humidity changes, then you can kind of visualize in your head the variation in speed with which the bearing expels grease. And that is why the equations for relube frequency and the equations for relube amount are very nice equations for theory and very nice equations for rules of thumb, but those equations are only 100% accurate where speed, load, temperature, and humidity are constant, which is pretty much nirvana, this place that our machines won't find themselves, right? So that's why using things like ultrasound to assist in how often we relube the bearings and what amount we put into the bearings when we relube them is so powerful. It's almost, we've made lubrication, condition-based lubrication, and I know that particular phrase, raises the ire on a lot of people, but the important distinction here is we add grease before the bearing is screaming that it needs it, because once the bearing screams that it needs it, damage is already done, and the damage is irreparable. So if we think about the relationship of bearings and heat, we got normal temperature. Some bearings heat up as they get bad, they heat up, and they eventually lock up because they've gotten so hot and they're swollen, and when everything swells, the clearances are gone, and it eventually locks up. Some bearings do that. Other bearings don't, however. Other bearings start to get hot. They'll level off for a while, and then they'll cool down to failure. So some bearings lock up, some bearings loosen up. So we have to remember that not all bearings act the same. Not all bearings in the same situation act the same. And if we can remember that some bearings lock up, some bearings loosen up, then the whole concept of applying ultrasound, vibration, tomography, oil, even motor circuit analysis actually becomes much more powerful, because we're not making the unsafe and incorrect assumption that all bearings lock up, all bearings loosen up. Not true. Some do, some don't. And for those of you who are would-be scientists, don't read anything into the scaling on this slide. It was just for illustration purposes. So nothing on that is intended to be accurate at all. It's just to show a relationship between temperature and bearing life as one set locks up and another set loosens up. So in light of that, this thing called prognostics, about knowing when bearings will fail, becomes kind of a sticky situation. It's almost nearly impossible. And it's almost nearly impossible because remember that in most applications, not all, but in most applications, speed, load, temperature, and humidity vary, and they vary drastically. And they vary drastically, so the rate at which the bearing expels grease and the loads that the bearing sees are going to vary as those things vary. So for prognostics to be possible, requires a steady state. Now, if you have a situation where temperature, humidity, speed, load are in a steady state, then you know, a certain degree of prognostics is possible. But this is a fairly rare case. You know, for every one situation where, you know, those 4 parameters are steady state, I can probably show you 9,999 other machines where those things are not steady state. So in terms of, you know, is it big enough and powerful enough technique for me to spend a whole lot of time worrying about it? I'm going to say that for the industrial generalist, the PDM technician that works on lots of different machines, the reliability or maintenance engineer that is responsible for lots of different machines in a particular factory, I'm going to say you shouldn't be worried about prognostics. Instead, we should worry about, is there a known defect, and did we detect it early on the P2F curve, and have we initiated the work execution management process to get that job, you know, planned, scheduled, and that defect eliminated before we have even approached any type of conditional, you know, increase in conditional probability of failure. So, and I was just mentioning the P2F curve, there you are, right? So now as we think about all of these different condition monitoring techniques and how we can use them to help us detect, you know, the different defects that happen in rotating equipment, I sometimes find it useful to split the P2F, or segment the P2F curve up into 3 equal zones. And it's not exactly equal there, but this is an artist rendition, so don't read too much into the relative scale or size of the 3 zones. But segment the P2F curve into 3 zones, and as we think about our inspection methods, as we compare things like vibration and ultrasound to oil and infrared to motor circuit analysis to visual inspections, or, you know, laying your hand on it or listening for it to be rough, right? As we make these relative comparisons between these inspection methods, ask yourself, in what zone would this inspection method find the defect? And we want to prefer, you know, zone 1 to zone 2, and we certainly prefer zone 1 to zone 3, right? So the earlier we can identify the defect, the easier it is to deal with it, the cheaper it is to deal with it, and the life just gets a whole lot better if we can detect those defects up in zone 1, and not till we get in, well, wait till we get into the edge of zone 3, where we painted ourselves into a corner. We painted our production counterparts into a corner where we basically offered them no other option but to roll the dice and see if the machine will make it until this particular order gets filled. So you hear maintenance people complain all the time. We make production aware of it, and they say, hey, you know, I'm going to run anyway. Well, there's a difference between making production aware of it 48 hours before they have to do something, or making production aware of it 3 months before they have to do something. If you wait and you only give me 48 hours, you've painted me into a corner. I have to roll the dice. I have to see if the machine will run until we get this order out. If you tell me 3 months in advance, and I look down through their production schedule, and I've got 5 or 6 different opportunities to get it resolved, hey, this is easy, right? So if we want to keep these zones in mind as we think about which inspection methods are we going to bring to bear on the different failure modes that we think are reasonable and likely for our equipment. Right. Not much different here. We're going to skip that one. If we can also split that P2F curve up into kind of a priority 1 through priority 5, right? If we think about priorities in our CMMS as a substitute for defect severity, you know, priority 5 is not a severe defect as a priority 3, which is certainly not a severe defect as a priority 2 or priority 1, respectively. So a way to think about how we convey the severity of a particular defect to, say, a production counterpart out in the plant or anybody else in the organization, we can still think of our P2F curve, but we can split that P2F curve up into, you know, the old standard, you know, priority 1 through priority 5 that a lot of people like to use in their CMMS, and we can use that as a substitute for defect severity. Right. Okay. So continuing on the idea of fault progression, then in zone 1, we've talked about this a little bit. You know, ultrasound is louder, but it's still pretty clean noise. It's very smooth sound. Vibration analysis have to use envelope demodulation to find them generally up in zone 1. When we move into zone 2, though, the ultrasound it's quieter, but it has gotten rougher. So the volume has went down, but the pattern of the sound has gotten, it's nowhere near as smooth. It's gotten rough. The vibration analysis, we no longer have to use envelope demodulation to find it. Just regular vibration analysis will find it just fine in zone 2. With respect to infrared, it's starting to warm up. In zone 3, you know, it's very rough ultrasound. It can be very hot. Vibration and ultrasound is very rough. It can be very hot, and depending on whether or not the bearing or gears are always, or most always oil lubricated, but depending on whether or not the bearing is oil lubricated or grease lubricated, we could add oil into zone 2 and certainly into zone 3, oil analysis as well. And if it's particular defects, we can even add online motor circuit testing into zone 2 if it's the type of bearing or type of fault that produces a torsional load on the drivetrain. Zone 3 if it takes a while, if it's got to get pretty severe before it creates that torsional load, like, say, a bearing locking up, for example. So I didn't intend for that slide to be just vibration, ultrasound, and thermography. The oil and motor circuit testing, it can be quite powerful as well under certain situations. But the idea of all of these is, if we think about the work execution management work stream, if you will, it always begins with work identification. How did we've got to go find the work. And we use our inspection processes, our inspection methods, or our inspection program, if you will, to find the work. So the inspections that mechanics and electricians do as a part of the PM program, that finds future work. The inspections that the condition monitoring or predictive maintenance group conducts, that identifies future work. Even our operator care program, if we've got operators and they have their own rounds of inspections, that finds future work. So if you can follow the logic here, if our work identification step is top-notch, then that enables all of the other steps, because you can think of these as a series relationship. In a series relationship, if one element fails, the whole chain's broken. So everybody has a work identification process, but some organizations, their work identification process is really bad. In some organizations, the only way they identify work is if the operator says, hey, this machine doesn't work anymore. Or if the operator says, hey, I happen to be walking by this machine and it is really loud, and I put my hands on it, it's really rough, and it's making a really weird noise. Right? So those work identification processes pretty much shoot the rest of the chain in the foot before they even get started. But if you think about some of the things we've been talking about, using ultrasound, vibration, infrared, oil, motor circuit testing, to find those, in this case, bearing defects is really close to point P, then the work identification process has become more powerful. And the work identification process has enabled all of the other steps in the work execution management process. So I really want you to give some thought to, like how strong is your work identification process? Are all of your inspections, up to snuff in terms of their ability to find the defect as close to point P as possible and enable that whole work execution management, or if you want to say planning and scheduling, to enable that whole planning and scheduling effort? So the beauty, the power of these inspection methods with respect to bearings in particular, the power of these inspection methods is it bolsters or improves that work identification process, and it makes all these other things that we generally lump under the banner or flag of planning and scheduling, it enables them. So not having it up to speed disables the planning and scheduling process. And it's so funny, we run into organizations all the time where they're like, our planners don't plan and it's very difficult to do scheduling, and and they think the answer is more planner schedule training, more planner schedule training. And then when you look at the quality of their PM program, the non-existent PDM program, and the fact that operators aren't involved at all officially in the identification of work, you say, well, fellas, while you might be able to do some polishing over their own planning and scheduling, your real problem is your work identification step. So we'll stop there. So if you think about it then, what all we're trying to do is enable this idea of planning. And for those of you who've never seen it laid out like this, when we first identify a defect in our bearings, if we can identify it as close to point P as possible, then we're all the way to the left. We're early priority 5. But the work request is initiated, converted to a work order. We research the job, order the parts, put the job plan together, so on and so forth. So as we're following that work execution process, that defect out there get a little worse, a little worse, a little worse with each passing day. Now, if we do this correctly, the job gets completed before it ever really becomes even close to an emergency situation. That's the way it's supposed to work. And identifying those defects close to P makes that possible. But if we look at people who don't have a good work identification process, and they're relying on what they see, hear, feel, and even sometimes taste to determine whether or not a machine is, quote, bad enough to work on, now they're in this situation. Things have to be expedited. Process has to be shortcutted. Job production schedule has to be rearranged. So you see all these sources for extra time and extra cost when we really didn't even have to put ourselves in that situation. The difference was simply the quality of the work identification process. Okay, so non-synchronous energy is the game. That's what we're looking for in bearings. Outer race, inner race, rolling element, faults, and cage. If you go back to those equations, the type of energy they're producing is called non-synchronous. Non-synchronous just simply means it is not a whole number multiple of turning speed. So let's take this fake spectrum here, and the blue line on the left represents turning speed of the shaft, and you see all the little harmonics of it, and we know that this particular pump is either misaligned or imbalanced because turning speed's too high, and that's accelerating the degree of fatigue wear in our bearing. So let's say it looked like that one month, but then very next month when we go to it, we see these extra little peaks pop up. Now you'll note that those little peaks don't have the red harmonic markers on top of them, which means those peaks are not an even number multiple of turning speed. Now, if that machine is setting kind of by itself, I'll just say if the vibration analyst has done their job, then those blue peaks mean there's a bearing fault. Bearings are the only thing that produces non-synchronous energy on the same drivetrain. So if I move my cursor to those, I find, and you can see it in the lower right-hand corner, I find that that is 4.943 times turning speed. That's what order means, 4.943 times turning speed. And when we looked up the, we didn't really have to, but when we looked up the bearing type, the bearing number, we identified that frequency as being the inter-race fault frequency. Now, we leave that long enough, that defect is going to transfer to the roller, which transfers to the outer race in no time flat. And so we didn't work on it the very next month. We came back, oh, look, we got a new peak over here. It wasn't there, now it's there. When we analyze that, we find that it's 3.057 times turning speed. Well, that's the outer race fault. Now here's the neat thing. We didn't have to know the bearing number. We don't really care that it's inner race or outer race on most machines. Some machines, I'll grant you the exception, but 99% of the machines out there, we don't really care. All we want to know is there non-synchronous energy in the spectrum? If there's non-synchronous energy in the spectrum, then we have a bearing fault. And if we have a bearing fault, we need to get it fixed. You know, so most of the time when people say, are you sure? We're absolutely sure. We got the bearing number, we matched up. It's an inter-race fault frequency, it's outer race fault frequency, it's cage frequency, it's ball frequency, whichever it is. Right? In that particular case, for those of you who are interested, the 4.943 and the 3.057, by the way, matches with an SKF 6311. So those are the bearing fault frequencies. In the ultrasound, if we were to collect a spectrum of the ultrasound for bearing with a similar fault and produce and display the spectrum, it's going to look something like this. And we can see we've got inner and outer race fault frequencies right there on the bearing. Another example of the same thing. There we go. There's a cage frequency, ball spin frequency, and inner race frequencies showing up in the spectrum from the ultrasound. So these are all powerful examples of, you know, finding those bearing faults using vibration, finding them using ultrasound. There's another one from ultrasound. So that after a while, they all tend to look the same, right? So we can also look at the bearing fault from a vibration and thermography perspective. The motor on the left is a 200 horse vertical turbine pump motor. Motor on the right, sitting right next to it, 150 horse vertical turbine pump motor. You can see the upper bearing on the one on the left is 153 degrees. The upper bearing on the one on the right is 119 degrees. This obviously caught our attention. We snapped the thermal images. I got the old vibration data collector out. Vibration pattern on the lower left-hand corner shows that, in fact, the upper bearing is bad. Lots of non-synchronous energy, lots of activity in the waveform, very severe, fairly severe fault. We found out that for a pure thrust bearing like in the top of these motors, you don't really have an inner and outer race, but you have a stationary race and a rotating race. And what we discovered was it's the rotating race that has the problem. You can see the comparable vibration data over the 150 horse, no problem. Normal, healthy vibration. So as we compare thermal images to vibration, one motor to the next, it becomes a very nice comparison between the two. Technology limitation. Here's a picture of a motor and pump with a belt tension problem. Newly installed motor. Shivs were very well aligned, except the belts were entirely too tight. Very, very too tight. And you can see the difference in the thermal images up top between the one on the left is just after installation, belts entirely too tight. The one on the right is after the belt tension has been properly adjusted. Now what's interesting here is vibration didn't show a thing. Ultrasound wouldn't have shown a thing. Why? Well, ultrasound won't work because we're looking for high frequency faults only, and shiv misalignment is a very low frequency fault. Vibration would have shown it if the shivs were misaligned, but the shivs had been very well aligned, so it wasn't the problem. Thermography shows the belt tension very, very well. So the lessons between that one and this one are, you know, there are some faults that some inspection methods show very well, other inspection methods don't see at all. In this particular case, the ultrasound was very quiet. The vibration showed misalignment and looseness, but we didn't really know why. But when we looked at it with infrared, it was clear that the coupling insert on the gearbox side, the left side, was just clearly the problem. So when we think about ultrasound and vibration and any of the other inspection methods with respect to bearing faults, we have to differentiate low frequency from high frequency faults. Low frequency faults are things like imbalance, misalignment, looseness, most coupling problems. Vibration finds them very well. Ultrasound can't find them at all because they're not high frequency. They don't produce high frequency signature. But the problem we have to worry about is that it's the low frequency faults that cause the high frequency faults. Unless the bearing's 8 or 10 years old, bearings don't just go bad. They go bad because of all those accelerators we talked about. Imbalance increased the radial load, misalignment increased the radial and axial load, all those other things that cause the bearings to go bad. So we have to balance our inspection methods between things that find high frequency very well and things that find low frequency very well. And the combination of the two becomes a very powerful team to not only determine is there a bearing that needs to be changed, but more importantly, why? Why does the bearing need to be changed? If we're not going to ask and answer the question of why does the bearing need to be changed and how can I prevent it and other bearing faults like it in the future from happening, then we're kind of spinning our wheels. So, we want to use these technologies in concert to help us, reduce those maintenance costs as low as they can be, identify and eliminate root cause, and afford the maximum time to plan and schedule work. So I really want to encourage you to think about your inspection programs for your bearings. And do we have the right inspection methods in place to identify those defects very, very high on the P to F curve, thus, making all these things we've been talking about possible? Or do we have the kind of inspection method that mostly relies on what we can see, hear, smell, feel, and taste in some cases, and as a result, we're very, very low on the P to F curve, and we cannot give the planning and scheduling effort the time they need to do their job. So we're a little bit over 3 minutes. I know I'm probably 10 minutes over because we need to leave some time for Q&A. But Maureen, what questions do we have? Anything?
All right. Yeah, we've definitely gotten some sent in, and if we don't get to all of them, which we probably won't, what we'll do is I'll get your questions over to Andy offline. He's always very kind to still follow up after the fact. So I'm going to throw that out there for you, Andy, to volunteer you to do that.
Sure. She's priming me.
Yep. So one question that had come up, someone was wondering, when they're working in a wet environment with cleaning chemicals, should you grease after every cleaning, or could that cause issues as well?
Oh, yeah. One of the other loaded questions in the bearing world, right? So
they probably all are.
So, yeah, I mean, sanitation is just a fact of life. It's something we have to do. So if you work in the food industry or the pharmaceutical industry, you eventually have to stop and clean your stuff, right? So I think I'll answer that this way. There are two big problems we see when people clean their rotating equipment. One, they've blown their seals a long time ago with how much they over-grease a bearing. And with the blown seals, no matter how I wash it down, I'm going to push cleaning solvent or water or both into the bearing. And if that's the case, then yeah, I've got to purge that somehow or another, because cleaning solvent and water just make terrible lubricants. And so we see a lot of increased failure rates of bearings around where the sanitation processes are, let's say, less than adequate. Right? And then another thing that's very closely related is we've got the water hose and it's spraying this hot water, sometimes even caustic solution, and it's under fairly good pressure, and we blow it just right into the bearings, axially in line with the shaft. We try to wash the end of the bearing because apparently got material on it, so it's got to be sanitized. But if we don't blow perpendicular to the bearing to the shaft, if we don't blow axially to the shaft, we blow perpendicular shaft, we decrease the amount of solvent or cleaning material or water that we're actually blowing into the bearing. So a lot of the bearing faults associated with sanitation have to do with blown seals that hadn't been repaired, and poor lubricant practices are blowing the seals. And then, you know, we're not taking care of how we wash down that equipment. It's one of those things where, you know, if I can't clean with just the hose in my hand, I'm not gonna. And so we see a lot of people where they should stop and get a brush. They don't, because I'm not picking up the brush. I'll clean with the hose, and whatever I can clean with the hose is what I'll clean. And if I can't clean with the hose, then hey, I can't clean with the hose, right? So I don't know who answered the question, obviously, and I'm not implying that your sanitation practices are like that. But let me just say that quite a bit of experience in that world, and those are by far and away the two main culprits of bearing failures as a result of, you know, poor sanitation practices. All right, what else you got, Maureen?
All right. This one, so I'm just going to read this one. You had showed the BFIR problem with the times turning speed, and they wanted to know if that was calculated with the given equation that you gave towards the beginning of the presentation.
Back on the slow speed one?
Yeah, I think so.
Yeah.
If that's not quite right, you can write me your question.
So,
okay.
You know, we don't have to calculate them anymore. If you got vibration software, you just punch in the bearing number, and the bearing, the software spits back the inner race fault. There we go. The inner race fault frequency, outer race fault frequency, that kind of thing. You don't have to calculate it anymore. In fact, you can go to SKF's website. They've got a fault frequency thing. You punch in the bearing number, and it tells you what the inner race fault frequency is, outer race fault frequency, you know, so on and so forth. Now, it also tells you the number of balls and pitch diameter and all that stuff. So if you want to do it the old-fashioned way, you can. But we hadn't had to do that for a long time. Now, between the software and the bearing manufacturer's website, they just go ahead and give you the answer. You don't have to do the manual calculations. So I'm sure I didn't do the manual calculations because I may have done those once or twice in the last 20 years. I always just look them up.
Okay, and they wrote in, that did answer their questions, so good, thank you.
Good.
Okay, and then let's just do one more, and then a couple of these that are left are pretty easy, I think, for us to just sort of give. It's more looking for additional information, which we can email some resources out after the fact. So here's one, you know, when you're talking about doing analysis on the level of lubrication, if you're not able to get close to that access point, you know, what are your recommendations for doing that analysis?
So we're talking about pulling an oil sample?
Yeah, exactly. I think that's what they were talking about. Yep.
Okay. You know, that's a real common one, and you know, I don't know if this person is going, you know, but some people don't like this answer, but if you can't get a representative sample that's not contaminated, then you have to, I'm not going to say re-engineer because that sounds like a bigger effort than what it actually is, but you've got to install some stuff on the machine so you can, right? So you've got to put some hardware on there that allows you to get that representative sample. So an example of that might be, you know, instead of a solid hose, you know, get you a hose made up that has a sample port in line with that hose, and, you know, on a down day, take the old hose off, put the new hose on, and now I've got a sample port that gets me a representative sample, you know, without, you know, it provides access so that I can get that representative sample, right? You know, sometimes it's as easy as a port on top for you to stick your, you know, your vampire hose, if you will, down in there and at a certain length and get that representative sample. But in short, if you can't get to it, you gotta make a little bit of investment in time, money, and hardware, and modify the machine in some way so that you can get to it. We see that all the time when we go out and we do a lubrication survey for companies, and part of the survey we come back is, yeah, you've got X number of pieces of equipment that you should be pulling an oil sample on, and a certain percentage of those, there's really just no way to do it. So we're going to have to you know, make a few suggestions on how to modify that machine so that we can get a representative sample. And for those of you who may be wondering, draining it out of the bottom of the reservoir is never a representative sample.
Okay.
So I don't know if that answers their question, but that's what come to mind when you phrased it. So.
All right. Well, I think we'll stop it there. I'm going to take the screen back from you. So thank you for folks that put in your questions, and feel free, because we've still got it up, if you have additional questions, this GoToWebinar system that we've got logs all of those, so I can go back in once we're done and pull any questions we didn't answer and either get you guys the information or get you over to Andy to get those answered. So as we're wrapping up here, feel free to keep popping those in and we'll get them answered offline. So Andy, thank you so much. That was really great. I'm already getting emails from people and comments that this was a really great webinar. So we thank you for taking some time out today to talk with our group. And I'm sure we'll probably be bringing you back maybe in the spring to do some more talking about bearings. It just seems to be a topic we can't get enough of. So appreciate you taking the time.
Thanks for the opportunity.
Awesome. All right, so I have just a couple closing slides here for those of you that are still with us. Just want to make sure you know to head over to uesystems.com for anything and everything to do with not just bearings, but all the other applications that ultrasound covers. We've got a ton of sound samples, which I know some of you were asking for, and just all kinds of information that might answer some of the questions that you might have had. We do have on our website all of our past webinar recordings, including in a couple days we'll have this recording. So if you had to, if you got in a little late or you've got a colleague that was tied up and couldn't make it, you'll get an email from me once we've got that online, so you can check it out again. Just a lot of resources there, and if there's something that you're looking for that you can't find on our site, certainly get in touch with us. We'll track it down, and make sure we can make it available to you. We want to make sure we stay connected, so feel free to hit us up on our LinkedIn group. We've got two different groups, our UltraProbe users group and our Reliable Asset World group. Lots of great conversations take place there, questions that kind of come up from events like today. So feel free to head over there, ask your questions, help answer questions. Just a really great forum for connecting with your peers around the globe. We're also on Twitter. We've got our Sound Advice blog, so lots of ways to stay connected in between these monthly webinars. Some dates to throw out to you. Our next webinar is actually going to be October 30th, and we're going to be talking about planning and scheduling. So kind of a little bit of a shift from these more technical presentation, but I think everybody can relate to needing to put into place good planning and scheduling practices. So make a note of that. We'll get invites going out soon. And then our conference, Ultrasound World, is going to be in its 10th year next May, and we're happy to be co-locating with Ultrasound World our brand new conference, Reliable Asset World. So we hope you'll check out the website for more information on that, and mark your calendars and make plans to join us in Florida. So with that, I'll leave this screen up here for a little bit so you can take note of our contact info. I think you've all probably gotten my email address, so if you need anything at all, any questions, just get in touch with us and we'll be able to help you out. With that, I'll let you all go. Have a great rest of the day, and we'll hopefully see you back here next month as we talk planning and scheduling. Thanks again to Andy, and everybody have a great one.